Every metro system solves the same problem: move millions of people through a crowded city. But some cities don't play fair. They pile their streets onto mountainsides, float them over rivers, or stack them above quicksand and solid bedrock. The engineers who answer get pushed to the absolute edge. These are the world's most extreme metros, the deepest, the busiest, the steepest, and the strangest ever built. To rank the extremes, we'll measure 4 things. How deep a station can go before the ground itself fights back. How many people a single kilometer of track can carry. How steep a slope a train can climb before its wheels simply slip. And how cleverly a railway can thread itself through a city with no room to spare. Depth, density, gradient, and structure, 4 limits, and the engineering that beats them. Start with depth. A metro doesn't burrow deep for the thrill of it. It's forced down by what lies beneath the streets. Soft, waterlogged soils can't safely hold a tunnel, so engineers keep digging until they reach solid rock or stable clay. The deeper that stable layer sits, the deeper the station has to go. And in a few cities, the ground pushes that figure to extraordinary numbers. St. Petersburg sits on the worst possible foundation, ancient buried valleys filled with quicksand and silt. To build at all, its tunnels had to plunge around 60 meters down into a layer of solid Cambrian clay. Sinking shafts through liquid quicksand meant freezing the ground first, pumping chilled brine through pipes until the soil turned to ice hard enough to dig. Its Admiraltyskia station ends up 86 meters below the city. In Kiev, Arsenalna station drops to 105 meters, for decades, the deepest metro station on Earth. It was driven that far down to cross the steep, water-bearing slopes above the Dnieper River. Reaching the platform means 2 long escalator flights with a hidden hall in between. But Arsenalna's record wouldn't last forever. Because in the mountains of Chongqing, a city built on near-vertical terrain, Hongyankin Station now reaches 116 meters below the street, the deepest in the world. The land is so steep that 2 of its entrances sit 141 meters apart in height. To climb out from the bottom, riders take a cascade of 7 escalators in series, an 8 to 10-minute journey just to reach daylight. Pyongyang went deep for a different reason. Its tunnels run beyond 110 meters down, mined through solid bedrock. But here depth was the point, not a side effect. Built through the Cold War, the stations double as nuclear blast shelters, sealed deep enough to survive a strike. A single escalator flight drops 64 meters in one go, a 3.5-minute ride from the surface to the platform. That raises a problem the surface never has. How do you move thousands of people up 100 vertical meters every minute, all day long? The answer is heavy machinery built like an industrial lift. Moscow's deepest escalators run over 120 meters in a single span, with more than 700 steps. Take a high-speed lift instead, and the air pressure changes so fast your ears pop, like a plane taking off. Deep tunnels hide another force. A train fills its tunnel almost completely, so as it moves it acts like a piston, shoving a wall of air ahead of it, the piston wind. Engineers tame it with relief shafts that vent that pressure up to the surface before it blasts across a platform. And because deep rock traps heat, decades of braking and friction slowly warm the tunnels, demanding constant ventilation just to keep them cool. Now flip from depth to volume. The second extreme isn't how far down a metro goes, it's how many bodies it can push through. And the most revealing number isn't total ridership, it's density. How many passengers each single kilometer of track carries in a year? By that measure, the busiest systems on Earth are not the ones you'd expect. At the top sits Cairo. Its compact network carries more than 19 million passengers per kilometer of track every year, the most intense load anywhere on the planet. Sao Paulo follows near 12 million, then Tokyo above 10. New York, with its sprawling 400-kilometer web of branches, spreads its riders thin at under 5 million per kilometer. Density rewards the short, packed line, not the giant map. Carrying that crush safely comes down to 2 technologies. The first is the signaling. Modern systems use communications-based train control, tracking every train continuously so they can run barely 90 seconds apart without ever touching. The second guards the platform edge, sliding glass screen doors that open only when a train is aligned, holding the crowd back and the airflow in check. Together, they let a line run right at the edge of its capacity. Scale tells its own stories. London opened the first underground railway back in 1863 and still runs 400 kilometers of it today. Beijing and Shanghai have since built the largest networks on Earth, each crossing hundreds of kilometers. And beneath Guangzhou runs the longest single tunnel of them all, more than 60 kilometers of continuous bore, a hidden river of steel under the city. The third extreme is the one gravity fights hardest, the climb. A steel wheel on a steel rail grips with surprisingly little friction. Push the slope past about 4 or 5% and the wheels start to slip, spinning uselessly instead of pulling. For most of railway history, that was a hard ceiling. A hill too steep for a train simply couldn't have won, unless you changed the wheel itself. The first answer came from Paris in the 1950s. Replace steel wheels with rubber tires running on concrete. Rubber grips 2 to 3 times harder, and suddenly a metro can climb. Lausanne's fully driverless M2 line uses it to scale a 12% grade straight up a Swiss hillside. The same soft tires do something else useful in Mexico City. They soak up vibration, protecting fragile old buildings on the soft lakebed soil below. Past about 15%, even rubber gives up, and the train stops relying on grip at all. In Lyon, Line C climbs a brutal 17% slope with a rack railway, a toothed rail bolted down the center of the track, and a cogwheel under the train that meshes into it like a zip. There's no slipping a set of gears. The teeth simply pull the train straight up the mountain. And for the steepest grade of all, you stop driving the train and start pulling it. Haifa's Carmelit climbs a 30% gradient as an underground funicular, its cars clamped to a steel cable, hauled by a stationary winding engine at the top. The genius is the balance. As one car descends, its weight helps drag the other one up. Gravity itself, turned into the engine. The last extreme isn't about depth or speed or slope. It's about space, fitting a railway into a city that has none left to give. When there's no room beside the buildings, no room above the road, and no room left to tunnel, engineers get inventive. They hang the railway in the air, or thread it straight through the architecture itself. Wuppertal solved it more than a century ago. With its narrow valley packed wall to wall, the city hung its railway above the river instead. Opened in 1901 and still running today, the Schwebebahn dangles from a single rail on 472 steel supports. The carriages hang below the track, so on curves they simply swing outward, tilting up to 15 degrees, leaning into the bend like a pendulum. Chongqing went further still. At Laziba, the monorail runs clean through a 19-story apartment block, in one side of floors 6 to 8, and out the other. People live directly above a working metro station. The trick is total separation. The track sits on its own pillars, ringed by a 20-centimeter air gap, so it never touches the building. With rubber tires and air springs, a passing train is quieter than the street outside. Medellin took the railway off the ground entirely. To reach steep hillside neighborhoods that no road or rail could serve, the city strung up cable cars, gondolas, and wired them straight into the metro as ordinary transit lines. A journey that once took 2 hours on switchback streets now takes about 15 minutes in the air, and each support tower needs barely the footprint of a parking space. Some metros are extreme simply for how far ahead they reached. Lille ran the first fully driverless trains back in 1983. Dubai built one of the longest automated networks with no driver at all. Shanghai's maglev floats on magnets at 430 kilometers an hour. And in Moscow and Budapest, stations were built like palaces, chandeliers, mosaics, marble, one of them now a UNESCO World Heritage Site. Step back, and a pattern appears. None of these records came from chasing a number for its own sake. Each one was forced, by quicksand, by crowds, by mountainsides, by streets with no room. The depth, the density, the gradient, the structure. Every extreme is just engineering bending to the shape of its city. The harder the ground pushed back, the more inventive the answer had to be. From 116 meters underground to a cabin swinging over a German river, the world's most extreme metros are really a map of human ingenuity under pressure. Wherever a city said it couldn't be done, an engineer found a way down, across, or straight through. Thanks for watching Learn Railways, and we'll see you on the next line.